Next topic is basis and its dimension. Basis. The vectors v1, v2 until vk in a vector space V are said to form a basis for V if v1, v2, vk span V and v1, v2 until vk are linearly independent. So in other definition, a basis is a set of linearly independent vectors that can be used as building blocks to make any other vector in the vector space. So we have the following procedure for finding the subset of S that is a basis for W equals to span S as follows. Step 1, form the dependency equation. Step 2, construct the augmented matrix associated with the homogeneous system of the dependency equation and transform it to reduce row echelon form. Then, the vectors corresponding to the columns containing the leading ones form a basis for W equals to span S. First example, given the set S, the set of vectors S in R4 where V1 is 1, 2, negative 2, 1, V2, negative 3, 0, negative 4, 3, V3, 2, 1, 1, negative 1, V4, negative 3, 3, negative 9, 6, and V5, 9, 3, 7, negative 6. So let's find a subset of S that is a basis for W spanning S. So let's form the dependency equation. So C1 V1 plus C2 V2 until C5 V5 is equal to 0. So forming its homogeneous system, C1 minus 3C2 plus 2C3 minus 3C4 plus 9C5 for its first equation. Then the following are the other equations. So correspondingly, it's augmented matrix. So we have 1, negative 3, 2, negative 3, 9 for the first row is equal to 0. Then, after such, you can reduce to its row echelon form. Reduce row echelon form that you can verify. So, the leading ones appear in columns 1 and 2. So, vector 1 and vector 2 forming the set a basis for W spanning S. So we have V1, V2 is equal to the first vector V1 subvector 1, 2, negative 2, 1 and V2, negative 3, 0, negative 4, 3 is a basis for W spanning S. Let's have example number 2. Find a basis for the subspace V of P2 consisting of all vectors of the form AT square plus BT plus C where C is equal to A minus B. So we have P2 is equal to its general form AT square plus BT plus C. Then let's make C is equal to A minus B. So we have AT square plus BT plus substituting for the value of C which is A minus B. So then regrouping with A's then B's, we have AT square plus A plus BT minus B. So we have the P2 is equal to A quantity T square plus 1 plus B multiplied by the binomial T minus 1. Then we have C1 quantity T square plus 1 plus C2 quantity T minus 1 is equal to P2. So we have C1 So let's equate it to the general form, a plus at squared plus bt plus c. So here we can see that t squared plus 1 and t minus 1 span p2. Given c1 multiplied to t squared plus 1 plus c2 multiplied to t minus 1 is equal to 0 t squared plus 0 t plus 0, we can say that c1 is equal to 0 and c2 is equal to 0. Therefore, t squared plus 1 and t minus 1 are linearly independent. So, the subspaces t squared plus 1 and t minus 1 form the basis of P2 equals to at squared plus bt plus c, where c is equal to a minus b. Let's have example number 3. Show that the set S t squared plus 1, t minus 1, 2t plus 2 is a basis for the vector space P2. So let's have the general form, at squared plus bt plus c is equal to a1 t squared plus 1, a2t minus 1 plus a3 times 2t plus 2. So that is equal to a1 t squared plus a2 plus 2a3 t plus a sub 1 minus a sub 2 plus 2a sub 3. So we can denote that a sub 1 is equal to a sub 2 plus 2a sub 3 is equal to b, a sub 1 minus a sub 2 plus 2a sub 3 is equal to c. So we can have the following values of a sub 1 can be a sub 2 is equal to a plus b minus c all over 2, a sub 3 is equal to c plus b minus a all over 4. So S is span V. To show that S is linearly independent, so we have a sub 1 t squared plus 1, a sub 2 times t minus 1 plus a sub 3 multiplied by 2t plus 2 is equal to 0. So we have a sub 1 is equal to 0, a sub 2 plus 2a sub 3 is equal to 0, a sub 1 minus a sub 2 plus 2a sub 3 is equal to 0. Then we can have the following values of a sub 1, a sub 2, a sub 3 equals to 0. S is linearly independent. Therefore, S is a basis for P sub 2. The set of vectors t raised to n, t raised to n minus 1 until t and 1 forms a basis for the vector space P sub n, called the natural or standard basis for P sub n. So we have example number 4. Given R3 and the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, show that the vectors form a basis for R3. So let's check for the linear combination of these vectors to form any vector in the space. So we have C sub 1, V1 plus C sub 2, V2, C sub 3, V sub 3 is equal to any A, B, C. So we can have C sub 1 is equal to A, C sub 2 is equal to B, C sub 3 is equal to C. So these three vectors span R3. So we can also equate the vectors into 0, having C1 is equal to 0, C2 is equal to 0, C3 is equal to 0. So these scalars are all equals to 0. They are linearly independent. The vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 form a basis for R3. So we have the following theorems. Let S be a subset of a vector space V, then the following conditions are equivalent. So S is linearly independent spanning set for V. Example is it is a basis. S is a minimal spanning set for V, and S is a maximal linearly independent subset of V. Minimal spanning set means remove any element from this set, and it's no longer a spanning set. So maximal linearly independent subset means add any element of V to this set, and it will become linearly dependent. So we have also the following theorems. Let V be a vector space, then any spanning set for V can be reduced to a minimal spanning set. Any linearly independent subset of V can be extended to a maximal linearly independent set. Equivalently, any spanning set contains a basis, while any linearly independent set is contained in a basis. Corollary: a vector space is finite dimensional if and only if it is spanned by a finite set. So we have next term is dimension. The dimension of a non-zero vector space V is the number of vectors in a basis for V. We often write dim V for this dimension of V. We also define the dimension of the trivial vector space 0 to be 0. So let's have example number 1. The given example number 1 a while back. So the dimension of the subspace W of R4 spanned by S is 2 because there are only 2 vectors in its basis in a set forming its basis. Let's have example number 2. The set S T squared T1 is a basis for P sub 2. So dimension of P sub 2 is equal to 3. So we have also R cube, the set of forming 1 0 0 0 1 0 0 0 1 has a dimension of 3. In general, the dimension of R raised to n is equal to n, and the dimension of R sub n is equal to n. In general, the dimension of P sub n is equal to n plus 1. Example number 3. So, it is S is a basis for P2. Then, its dimension is 3. Example number 4. Let V be the subspace of R sub 3 spanned by the 3 vectors V1, V2, and V3. Thus, every vector of V is being formed by A sub 1, V1 plus A sub 2, V2 plus A sub 3, V3. So we can observe that V1 plus V2 is equal to V3, thus S is linearly dependent. Moreover, S1 equals to V1, V2 also spans V, and S1 is linearly independent. Thus, S1 is a basis of V, and its dimension is 2. So let S be a set of vectors in a vector space V. A subset T of S is called a maximal independent subset of S if T is linearly independent set of vectors that is not properly contained in any other linearly independent subset of S. So that's all. Thank you for listening.